Okay.
Recording is on.
Okay. Hi everyone. So today we are going to discuss graph problems. So let me share my screen. Not graph trees problems. The BST. Share. Let me share. Okay. Can you see my screen?
Yeah.
Okay. Awesome. Okay. So last week we discussed about binary search tree and finding an element in binary search tree, right?
Yeah.
So this week we are going to discuss how to insert an element in the binary search tree. So what is the algorithm to insert an element and delete an element? Because if you look at this binary tree, it has its own properties, right? So it's
Mm.
not like a normal tree where you can insert anywhere. So it needs to follow this pattern, right? So when we are inserting, make sure after inserting the binary search tree, it still maintains that the rules of binary search tree, where every left node is greater than its root, and the root where every left node is less than its root, and root node is less than or equal to all the right children, right? That property need to be maintained. So when you insert an element, you need to find the right place where you need to insert, and then you have to insert an element. And also when you are deleting, if you delete some node, you need to make sure the tree is again BST after deleting. If you are deleting a node, what we need to do, we need to replace that value, right? Because if you are deleting a node, that node contains a lot of children, right? So in the BST, we need to find appropriate children that we can place at that location. Okay, so that is the deletion. So after deletion, there is a post processing work we need to do. So find Inorder Successor. This is also very popular entry program, so entry algorithm. So it's like Inorder Successor. What is Inorder Successor and why we need to find it? All these things I will explain. So this is part of the deletion actually. So in order to delete an element, after deletion we need to execute this algorithm Inorder Successor, and I will explain those as well. Okay, so let's start with the with the BST. What we have, this is the one last week we discussed about it. So where is it? Here is here is here is the tree. So let's write down that tree here. So 15, 3, 17, right? 2, 14, and 16, 18, right? So we already know the BST. If you write in order, that will give you increasing elements, right? The elements in sorting order, right? So in order, what is the in order for this?
2, 3, 15.
14, right?
Oh,
14.
sorry. Yeah, 14. Yeah,
In
14.
order is always like left root and left
That's
root
right.
right,
That's right.
and then again we completed
And
left
then
part and then root
and
15.
then 15, and then 17, 16, and oh, sorry, 16, 17, and 18.
Exactly, 16, 17, 18. So whenever you are processing a subtree, again you need to go to the left again. So that's why we will get in a sorting order. So if you look at this, it's completely sorting order of the elements, right? So now let's look at the algorithm where we need to include, let's say, insert 13. Okay, we already last week we did these algorithms, right? Like find 16, find 9. So if you want to find 16, what we need to do, let's say if you want to find 16, you start from root, always start from
Yeah,
root, right?
I'll start from root, and I'll check whether the 16 is greater than root or less than root. If it is greater than root, I'll go to the right side
Mm-hmm.
and check with the next number. And the 17 is greater than 16. So 16 must be somewhere in the left side of 17. So I'll
Exactly.
go to the left and find the.
Yeah, you will find that, right? So this is the way of finding it. So now let's look at the algorithm where we need to insert 13. So we need to insert 13, and like here is the insertion algorithm. In order to insert, we need two things. First one is root. Give me the root. Root is 15, and the value we want to insert is 13, right? So
Yeah.
we are giving a reference to the root, and the value we want to insert is 13. So
Mm.
how to insert a 13? Because if you look, this is, it follows a similar pattern, right? If the 13 needs to insert, where we need to insert, it should be on the,
Uh, Left side of 15.
exactly, because the value is less than the value of the root. So without changing the root, like we don't want to, the main intention here is we need to achieve insertion or the deletion with an optimal way. You don't want to shuffle so many elements, right? Because
Okay.
you can also put 13 at the root and down push the 15 to left or something. You can also do that, but that will make lot of efforts. You need to shuffle lot of elements. So that's why we don't want to, as long as possible, we don't want to change the existing tree. We will find the correct location and we will insert the value. That's the main intention. So now if you look at 13, so we want to insert 13. So we will compare with 15. Since it is less than, we'll go here. Then we will compare with 3. What will happen? So 3 is less than 13. Then 13
Mm.
should go to,
Right side of 3.
exactly, it should go to the right side of that, right side of 3. Now it comes here 14, right? Now again we need to compare 14 and 13. So it has to go to,
Left side of 14.
exactly. So that's where we need to go to left side of 14. So now if you want to go to left side of 14, the problem here is there is no more nodes, right? So
Yeah.
left side is like empty. Why it is doing this? Okay, now let me do this again. Yeah, so this is better. So now we need to put left side of 14. So now
Mm.
let's see, do we have any nodes? There
No,
is no
it's
nodes,
none.
right? Then we simply insert the 13 there. Correct?
Yeah.
So now if you, so now we need to check, is it right way to do? Because if you do the in order, we will get the sorting order, right? So let's see the in order. So what is the in order for this? Again, it always starts with the leftmost node, right? So
Yeah.
2, 3,
3,
and then instead of
2,
14,
3.
we should not process 14. We have to go to the leftmost node,
Yeah.
right? So 13,
2, 13, 14,
14, 15, and so on,
15.
right?
Yeah.
So we are in a good shape. So after inserting, we need to make sure it
It
follows
is
the same pattern. The in order, when you do the in order, we always get the sorting,
sorted.
sorting of the elements, like kind of increasing order of the elements. So that is the insertion. So now let's say you want to insert. Okay, there are no more insertions here. So let's look at so now let's say you want to insert. Let's say you want to insert 19. So how do you do that? So similar pattern, right? So 19, that means you compare with 15. So it has to go to the right side of the subtree, right side subtree. So you compare with 17. Again, it should go to the right side of 17, right? Then you compare with 18. Now here 18 is less than 19, right? Where it should go? It should go to,
Right side of 18.
exactly. That's where we will insert the thing. So now um, if you look at this one, so here what we are doing is this particular insertion algorithm, it's a like recursion. We need to be very careful while doing this. So these algorithms are recursion algorithms. So what we are saying is, in a simple way, let's start with 19. So you want to insert 19, right? So we will compare with 15. Okay, now 15, let's assume that 15 is the only element. If 15 is the only element, what you do? Simply, let's say this is root.
Simply,
Okay,
uh,
you will insert at the r dot
right. Yeah.
right, r dot right equal to 19, right? So the algorithm works that way. That means when you are comparing with a node, you are seeing if this is if the number is bigger element, you simply say, hey, insert 19 at the right side of this one and give me the value, so that I will attach to my right. So what I'm saying is, so since the value is greater than the root, I'm saying root dot right equal to, now insert an element somewhere here. So now the problem becomes like inserting an element for this tree. So what I'm saying is a recursive way. So first, the when you start the program, you need to insert the 13 for in this tree. Correct? Is it right?
Yes.
When you start the program, sorry, you need to insert the 19. We are talking about 19, right? So when you start the program, you want to insert 19 in this entire tree. Correct?
Mm. Yeah.
Now, what you are doing is you are starting with the root. Now you figured out root 15 is less than 19. That's why what we are saying is, now insert 19 somewhere in the right side, somewhere in the right side. This is right side, somewhere in the right side of 15, and give me the right node, because you don't know, maybe if there is no nodes, you the 19 will come here, right? If there is no nodes, if there are some nodes, you need to put 19 at the right location, and 19, maybe this will also change, we don't know, right? So that's why what we are saying is r dot right equal to insert node in the right side. So now I'm going to say 17 and 19. So what I'm saying is, the insertion node here, right? Insert node, what are we sending here? In the insert node, we are sending the root node and then the value which we need to insert. Correct? So we need to send two things. First one is we need to put the root node. We need to give the root node and then value we want to insert. So
Okay.
initial in the initial in the, when you start the algorithm, we did the same thing. Insert node SERT insert node of root. What is the root value? 15. And what is the
15,
value you want to insert? Here is the 13. Let's say you want to insert 19. So you
19.
want to insert 19. So you are sending a root value, and you are sending the, of course we are sending the root reference here, not the value. So you are sending the root, which is the value 15, of course, which has a value 15, and you are sending the value which you want to insert, which is 19. Correct? Now, since you figured out 19 should go to the right side of 15, so this insert node will returns the node object. So what it means is, you are going to insert 19 in this tree, and you are going to update the tree, and finally it will give the root of the tree. Okay, that means, so you are going to update the tree, right? You are inserting, if you are inserting an element, tree will get updated. How you update is up to you. You can put 19 on the top. If you want, you can shuffle the elements whatever the way you want, right? You can also put 19 on the root. Why not? Only thing is, if you want to put 19 on the root, what you need to do is you need to push the 15 to the left side. Correct? Isn't it?
Yeah, we have to replace the.
Elements, yeah.
Yeah.
If you are putting 19 here, the problem here is, if you are putting 19 at the root, you have to remove the 16 and 17 also, because they should not be on the right side. You need to pull those 17 and 16, and you need to place somewhere in the left side. Correct?
Yes.
That is also an algorithm. You can also do that way. So it doesn't matter how you do. I know that is not an efficient algorithm, but it's up to you. So I am asking only one thing. Insert a node. Here is the root, 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 and here is the element you want to insert, and give me the final root element which you want to return. You can put 19 at the top, You can put 18 at the top. It's up to you. But what this insert node need to return is the again the updated root value. So you are inserting and you are updating the tree. Once you are updating the tree, I'm expecting the updated root. What is after updation, after insertion, you do all the shuffling, you do whatever magic you want to do, and finally give me the root. Okay. So that's what the answer here. That's what the return value here. What I'm saying is you are going to give a root. I'm putting in the same variable n15. Okay, so I'm giving n15, which is the root. I'm assuming you're going to give the same, otherwise it's okay. You can, if you give the 19, let's say you inserted the 19 and you are giving the 19, so n15 is becomes the value 19. It doesn't matter, right? I am overwriting the root value here. Why I am doing is I will explain. So the reason here is it's a kind of recursive problem here. Recursive problem. So you are inserting 19, you started with 15, right? Now you, as I said, you figured out 19 is greater than 15. So now you no need to look any of these elements, right? Because you know that 15 is already at the root. That means 19 should go to the right subtree, right? 19, you just said like 19 should go to, this is the right subtree. It can be 3 elements, it can be 10 elements, it can be 100 elements, we don't know, correct? So
Yeah.
now what are we doing here is, now root dot right equal to insert node, again insert node of, now we are going to insert 19 starting in this subtree. What is the top of this subtree? What is the root element in the subtree?
17.
Exactly. We are going to say, hey, here is the, take this root dot right, and 19. So what are we doing here is we are calling the same method. We are calling the same insertion method, but we are sending the update. We are sending the different root value. Now consider 17 as a root and trying to insert 19. We are asking the same method, we are calling the same recursion method. We are saying, hey, now take 17 as a root, please try to insert 19. Okay, so now it will execute the same way. Now what happens, 19 is again greater than 17. So now what happens, 17 dot right equal to, again insert node 17 dot right. What is the 17 dot right now? 18 and 19. So basically, again, I'm giving this subtree. I'm giving, because 19 is greater than the root 17. I'm giving this subtree. Now 18 is the root. Insert 19. Got it? Now
Yes,
do whatever
Suresh.
you want. Do whatever you want to do. Finally, that will be the 17 dot right.
Okay.
You can put 19 here and you can assign 8. You can push the 18 to the bottom. Now 17's right is 19, correct? You can also do that. So that's why we are saying 17 dot right equal to insert node. What is the right value? 18 and 19. So we are calling the same method by updating the root value. That's the main catch here. The algorithm is just 5 lines or 6 lines, very small, but we need to understand how this will work. Okay.
Yes. We are not altering any structure in this. We are just inserting it.
We are just inserting. After
Yeah.
inserting, there is a chance of structure change. There is a chance, right? So as I said before, so now the diagram is so messy here. So what I'm saying is, previously we have 18 here, right? So we have
Yeah.
18. So there are different ways of insertion, right? So 18 is here, I'm asking to insert 19. So either you can put 19 here, or you can also put 19 here and push the 18 here. That is also possible, right? So now it still follows the BST, because after 17 it goes to 18 and 19. So in this situation, what happened, 17 dot right changed, right? 17 dot right is until now it is 18, but now after you insert 19 here and push the 18 here, now 17 dot right became 19, right?
Yes.
That is what we are doing. 17 dot right equal to insert node. Do whatever you want to do, insert the node and give me the updated root. Give me the root, whatever you updated. It could be 19, it could be 18. That will be the right side of this 17. Okay.
Yes. Yeah.
That is the algorithm. So here is the ending point here. So in this situation, right, in the earlier situation where we have 18 here, now you need to put 19. What is the, when are we going to put 19? If it is null value, if the 18 dot null, if it is null value, you are just place the new element and return that element. Because something like this, if the value is like this, so now you came here 18 and you want to put 19. It follows the same pattern. 18 is less than 19. That means 18 dot right equal to, because it goes to the right, because the 19 is bigger. So 18 dot right equal to insert node. We'll call the same method. Insert node. What is the existing right? Null, comma 19. We will call the exact same method with null value, because there is nothing for 18 dot right. Correct?
So null value will be called.
Yeah, because 18 dot right, existing right is null. We don't know 18. When you are running the algorithm, you are looking at the tree. Now you are saying, hey, the 18 doesn't have any right node, 18 doesn't have any left node. But when you are running the algorithm, we don't know, right? So we will call the same method. 18 dot right equal to insert node in, insert node 18 dot existing right, whatever the existing right value. If it could be, let's say it could be 20. If we have 20, we'll say 20. But if it is null, we'll simply pass the null, whatever the value here. We are sending null value here and 19. Now what happens is, since the root is null, since the root is here, then nothing here. You no need to compare. You, if the value is null here, just return the 19. That means create the root that will be the right side of this node.
Okay. Yeah.
It is very slight logic change there. Because there is no tree. You are saying like, hey, insert a 19 in an empty tree. There is no tree here, and you want to insert 19. That means just put the 19 at the root and send that value. That will become the 18's right. Okay. Now, if I show you the algorithm, then it might be easy to understand. So here is the insert node. Okay. As I said, it returns the node. Okay. And here is the root value. It's a root node. Here is the root node. And here is the value you want to insert. First condition. That's what I just said, right? The first condition is, if the root is null. If the root is null, there is nothing to compare, right? If the root is null, you are asking me to insert v in a root in a tree where the root is null. If the root is null, here is the element you are going to create. Here is a new node, and new node value, I am sending the new node. If the root is null, hey, take this node. This is the root value, right? Else, that means it's not null. Root has some value. Root has some value. If the value less than root value, root dot left equal to insert node root dot left comma v. Else root dot right equal to insert node root dot right comma v. I just said this one, right? So basically, if the value is less than, if you are going to insert 13, you are saying, hey, take this entire subtree. How are you going to? So 15 dot left equal to, that's what it is, right? Root dot left. 15 dot left equal to insert node 3 and 13. you are giving the left here. You are already giving the existing left. Here is the existing left, and here is the value you want to insert. Following?
Okay. Yeah, Suresh.
It is quite difficult to understand at the first instance, but if you are
So, uh,
thinking, yeah,
yeah, I have one doubt actually.
yeah,
We are going to insert the new node, right? Yeah,
yes.
it's a new node. So, how come you can insert V in the right thing actually? V is just an integer as per.
V is an integer, but we are creating a node here. Look at this. If the root becomes null,
Okay. Okay.
so it will go all the way until it finds a null value. So
Okay.
when you are inserting 13, right, you cannot insert at the place of 3. It has to go to either right or left. So since 13 is
Mm.
greater, it will go to the 14. Now 14's 14 is less than 13 or greater than 13. It's a greater than 13, right? Now
Mm.
14 has to go to the left. That's what it is happening here, right? If the
Okay.
13 has to go to the left of 14. So
Uh,
that's the comparison
in
here.
that case, it is a null, so a new node will be created and it will be assigned there.
Exactly. So now let's say value. Now, if you are at the 14, right? If you are at the 14, what happens? So value is 13 less than root dot value. Root is 14, which is value is 14. So 13 is less than 14. Correct?
14. Yeah.
Now what happens? 14 dot left equal to, this is 14, right? So
Yeah.
14 dot left equal to insert node. You are inserting node. So there is no 13 here. Insert node. You are calling the insert node
Null.
with the root dot left. What is the left value? Null.
Null.
So null, you are calling the same method with null and 13. So now what happens? It comes here, root value is null. Now it will create the new node and that new node will be returned. Now root dot left equal to that node you just created.
Yes.
Now root dot left means 14. 14 dot left equal to 13. So 14 dot left equal to 13. So now that connection is established here. Now you are returning root. So what happens here is you already updated 14 dot left. Now you're returning 14. So now 14 becomes the 13 dot left, 13 dot right. Now 13 becomes, no, it's not 13, which is 3 here. 3 dot right equal to 14. Now 3 again returned here. 3 returned here. 3 becomes the left of 15. So it will update the pointers again. Finally, it will return the 15 back to the program. Okay, so it happens a similar way for the right side. So I can execute and see you how it works, because it's a very tricky, but it requires some practice to understand. So let's see. So here is the insert node. Okay, now let's run start debugging. It's a recursion, right? Recursion is always like, you know it will go and go into this different levels of execution. We need to see how it works. Okay, so now let's look at insert node here. Let me put a breakpoint. Okay, continue. Okay, we are inserting. So we already here is the tree which is in a increasing order, right? Now we are inserting with
13.
root value 15 and we are inserting 13. Correct. See, what is the root value? 15.
15. 15 is
15
not
is
equal
not
to
equal
9.
to null, right? It will come here, else case. Now, what happens? Let's put that breakpoint everywhere. So now, root value is the fifth is with the value which we want to insert is 13, and the root value is 15. So which is good. So that's why it will go to the root dot left. Okay,
Mm.
see this root dot left. Root is 15. Root dot current left is 3, right? If I go
Yeah.
back to here, this is what we have, 3, right? So we are sending that. as a updated root. You are sending the, like you are calling the insert node root dot left, which is the value 3 and the value 13. This is the value you want to insert, right? Now if I continue, what happens? It comes here. Now what is the root here? Now root
Now
is
the root is 3.
exactly. Now root is 3, which is not equal to null. Now it will come here. Now the value you want to insert is 13. Is it less than or equal to 3?
No.
No, because 13 should go to the right side. So
Yeah.
if I remove some of these arrows, you can see, right? So here what we have here is 2 on the left side.
14 on the right side of 3.
Yeah, here is a 14 and here is a 2. So now you want to insert 13. 13 should go to the right
Right
side.
side of 3.
Right side of 3.
Yeah.
That's why it will go to the else case. See
Okay.
this. So root is 3 right now. 3 dot right equal to 14. 3 dot right is
Mm.
14, but we are overwriting that with by calling the same method. Hey, take the 14 as the new root. Okay. Insert 13. So we are giving root dot right. What is the root dot right? 14. We are giving this node as a new tree and asking to insert 13. Okay. Now it will go to the same method again. So now what is the root value? 14.
14.
Okay. Now we will see, is value 13 less than 14? Yes. So 13 has to go to left side of 14, right? So
Yeah.
that's what will happen. So 14 dot left, which is series. What the root is 14. 14 dot left. What is 14 dot left currently?
14 dot left is null.
Null. So that's what it is. You see that it is showing as null. 14
Okay.
dot left equal to, we are calling the same method. Insert node 14 dot left, which is null, and the value 13. Okay.
Okay. Null. Now the first condition will get.
Exactly. Now the first condition is null. You are saying now you now you are asking me to insert 13 in a empty tree. There is no tree to compare. There is no elements to compare anymore. Now what are we going to do is we are going to create a new node
You know.
with the value 13.
Okay.
So now we created a new node. This new node has the value 13, which is the value you want to insert, right? With the
Yeah.
left and right null. That those are the default values anyway. Left is null, right is null. Now that is going to return back to the, see if you look at the stack trace here. See how many calls, this is a recursive call, right? See
Yeah.
now it will go back to the 14. See, we are returning that root, right? We are returning the value c. So because now root dot, now if you look at here, root dot left equal to 13. So the root
Yes.
value here is, now you are at the 14. Now that's a return. That's the thing, right? If you are in a recursive program, once you complete, it will come back to here. So now what
Mm.
happens? Root value is 14 and 14's left equal to 13. 14's right is still null. You did not execute this. You did not insert anything to the right of 14.
Yeah.
Correct?
Yeah.
We inserted only at the left
13.
side of 14. Okay. So
Yeah.
now we are returning 14. That 14 will go back to 3. So 3 dot
Mm.
3. If you look at 3, 3 dot left is 2, 3 dot right is 14.
Okay.
We are just returning the same values. We are returning 14, we will return 3, and we will return 15. So if I go back again, continue, now see this. Now the value is 15. 15 dot
Okay.
left equal to 3, 15 dot right equal to 17. Nothing changed here. So we are
Mm.
updating, we are just returning the value. So now finally you are returning 15 back to the algorithm. See, now and 15. Essentially, you did not change anything. You could put 19 or 13 at the top, but we did not do that. That's not an efficient algorithm, right? You find the
Mm.
exact location. You found the correct location of 13, and you just assigned 13 at the correct location. You did not change any
Okay.
of the existing nodes. Okay,
Current look. Hello.
are you following?
Suresh. Ah, yeah.
What happened? Any question? And do you
Mm.
have any?
No, 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 nothing, nothing. In the meantime, I couldn't hear you. That's it.
Oh, okay, okay, sorry. So now you understand, right?
Yeah.
Basically, we created a entire tree without updating or without modifying the existing nodes. We added 13 at the correct location, right? Are you following?
Yeah, yeah, Suresh.
Yeah. So that's why we got the same value here. After inserting, after calling the insert node, you got the n15 is still pointed to the 15.
Okay,
Value 15, because you did not change the existing values, you did not move the, or you shuffle the any elements. Okay,
okay.
so that's how it worked. And now if you print after 15, like when you are printing now here, let's see. So now here is the here is the values. Where is it? Console dot right. Yeah, here is the values after inserting 2 3 13 14 15
14,
16
15,
17.
16, 17,
So
18. Yeah.
basically 13 got inserted as a left of 14. That's
14.
what it here, right? That's why
Yeah.
we got the in order. If you process the in order, we'll get 2, and then 3, and then 13,
Then
and then
13, 14, then
15,
15, 16, 17, 18.
18. Yeah, that's how it. That is the answer, right? So we are
Okay.
calling this in order, print in order. So I'm just calling the print in
Insert.
sort order, which is like
Okay.
print in order. I'm
Mm.
calling that method, which is something I showed last time, right? Which is
Mm.
just in order traversal.
Okay.
Okay. So now
Yeah.
that is the main part of the insertion. Now
It's a bit tricky, but it's easy.
it's
Insert is
tricky.
easy.
Exactly, very tricky. But writing this is easy. But we need to look at exactly like the return value is very important. If you don't, if you are writing like if you are returning just void, or like if you are not returning, you cannot even insert properly,
Okay.
right? Because it has to be like this. Either if the value is less than the root, so root dot left equal to new value. If the value is greater, root dot right equal to new value. So unless you are updating the left and root, it never be inserted. If you are just creating a node, right, there is no point of just creating a node. It has to be linked. That new node, either it should be linked as a left of root or right of root.
Okay.
Correct. So if you are
Yeah.
if you are calling this left of root or right of root, you need to change the return value of this method is also node.
Yeah.
So it's a recursive function. Like, is it possible to do without recursion? Maybe, but it's really tough because we don't know how many nodes. Like it's the same program, right? Like the recursion. Why are we doing recursion here is, so once you figure it out, once you feel, let's say you want to insert 13. So once you figured out 13 should go to the left side of 15, it's exact same problem.
Yeah.
Again, it could be
Same.
another 10 nodes or 100 nodes or million nodes. The program becomes like, hey, you need to insert 13 in this tree.
Yeah.
It's the same program we are executing on a smaller set of values. That's why it is
Yeah.
recursion. Why it is
Okay.
recursion
Repeating the
is,
same steps of instructions again and again.
exactly, exactly. Only thing is you are figuring for every step. At every step, you're finding whether you need to consider left subtree or right subtree, left subtree, right subtree, left subtree, right subtree. It will go to the every root and compare. That's what we are doing. Here is the comparison, right? So if you look at the find node is also same thing, right? If you are find node, we did the exact same thing, but the only thing is boolean. We are returning just boolean value.
Boolean value.
but here, since we are updating it, right? So you need to say either it is left or right. So if you look at here,
Yes.
see, if the root is null, false. If the root value is null, you did not find a value. This is the value you want to find, but root is null. If the root is null means either there are two conditions. You gave the empty tree, or you reached all the way to the down where there is no more values. Correct?
Yes.
So initially we figured out like 19. 16 is there, but found 9. Did you find 9? No, because you went
No.
all the way down. Finally, you end up reaching a null values. So you're returning false. If the root has some value, you are comparing here, right? If the root value equal to the value you are looking, return true. This is exactly the same comparison in the insertion node. Otherwise, if the value is less than, of course, this is the exact same comparison. We no need to compare values in the root in the insertion. Why do you need why do you no need to compare for equality? Equal, because it can go
You're
either way.
not.
Let's say if the value is less than if the value is equal to root value, what happens? It will be inserted to
Stops.
the
We
right.
need not insert it.
No. It will go to the right side. Look at here.
Oh,
If the value is, let's say you want to insert 17. You already let's say, yeah, here is 17, right? 17 is already there. If you are
mhm.
inserting 17, is 17 less than 17? No. So it will be
No.
inserted to the right side of 17. So that could be okay. So this is also binary tree. So let's give an example here.
In
So
such case, 17 will be inserted twice. Is it so?
yeah, it's okay. So that's how the binary tree is, either like this. So left less than root, and root less than or equal to right. So this is also
Okay.
binary tree. So 14, 15, 15.
Okay.
So it's okay. So there could be duplicates, right? Let's say
Okay.
you want to insert employees with age. So there will be two employees with age 25, let's say. But are you not going to insert that employee object? Hey, we already have an employee with 25, so I'm not going to recruit you,
No, we will
right?
insert
So
that.
we can put somewhere. Either it will go to the left or right, we'll follow that, right? Let's say in this algorithm, what we are doing is we are putting in the right side. So because if you look at if you compare here, right? See the 14 and not equal to 14, it will go to the right side. No problem. It follows the same pattern, right? So here is the thing. So v is root dot in the finding. What are we doing in the finding algorithm? We will go, if the value is less than, it will be somewhere in the left side, right?
Okay.
If the value is greater than, it will
It
be
will
somewhere
somewhere.
in the right side,
Okay.
right? We are calling the same method. We are calling the same find node method by just changing the root value, not by just changing the root node. So instead of starting at the root, find from the right side, right subtree. If the value is less than, find the node in the left subtree, right?
Okay.
It follows the same pattern, but only thing is you are updating the values
Fine.
here. This is the only change. So it will change the return value here, and after insertion, you are going to update the proper node, left node or right node based on the value. Okay.
Okay.
So we can try inserting duplicate.
Okay.
Now let's say you inserted 13 here, right? Let's see what happens if I insert 13 again. Or let's see. Okay, so we have 15. Let's say, let me write it down. 2, 3, 14, 15. So we have something like this, right? 15, 2, 3, 14. And what is the other thing? Is it 17? Yeah,
Yeah,
17.
17.
17
17,
here,
16,
16, and 18,
18.
right? So now let's say you want to insert 17 again. Let's see what happens. Okay. So if you want to insert 17, where it will go?
It will come under the 17, the right side of 17.
Yeah, 17. So it will compare with 15. So it will go to the right subtree. Now again 17 less than 17. So here is the 17. So if you compare, if you are here, right, the root node here. So the value is 17, but root value is also 17, which is not. So that's why it will go to the here, root dot right. So now it will try to insert 17 here. Now what happens? Now root value is 18, where it will be inserted?
Right side of, sorry, left side of 18.
Left side of 18. That will go here because 17 is less than root. So 18, like 18 dot right left equal to, you know, 18 dot left with 17. 18 dot left is null, so 17 will be inserted here. So now it will be, if you compare in order, still in a sorting order, right? 2, 3, 14, 15, 16, and then 17. After this 17, it will go to this 17 and 18. It's okay, right? If the two people have 17 age, they are in the same order, right?
Okay.
So we always need to make sure it is in a sorting order. So 17, 17, 18, which is also sorting order. After 16, there are two people with age 17, and then we got 18, right? So we can try that out. So instead of inserting, after insertion of 13
13.
here, now I'm going to insert 17. Okay. So 13 inserted at the left side. Now I'm going to insert 17 here after insertion of 17. So let's put here run without debugging. Okay, it's still running, still building. Okay, why it is taking that much time? It's still building here.
But we have not pointed on 17, Suresh. You have pointed on delete node.
Huh?
Yeah, you have pinpointed on delete node. Yeah, okay. 17.
So I just ran without debugging. So now let's see. Okay. So now here is the first tree, right? 2, 3, 14, 2, 3, 14,
15.
15,
Yeah.
everything. And after
Yeah.
inserting, the 13 is inserted before 14. Now after inserting 17, see this one, 16, 17, 17, 18. So it was inserted at the correct location, right?
Yeah.
Yeah. Now, now is it clear? The whole
Yeah,
inserting.
it's clear. Yeah.
Yeah, it is tricky though, but it requires a little bit review and understanding how this works. Okay. Now delete node, which is complicated than insertion.
Okay.
Why? Because you are deleting a node. Insertion is something you can insert at the location where you can go all the way to the end of the tree and you can insert, right? But let's say you want to delete. The deletion is a bigger impact. Let's say you don't have 17 here. Now let's say you want to delete 17. Okay. If you want to delete 17, you cannot leave the other nodes, orphans, right? So if you just insert like this, if you delete this node 17, okay. Now how the 16 and 18 connected to 15? So if you are making this null, right? If you are making this null, there is no way you can reach 16 or 18, correct?
Yeah.
So that is the problem with the deletion. That is the problem. So how can we do that? So now if you want to delete 17, can you tell me how can we do this? There are two options here. What can you tell me? What are the options?
Yeah. Replacing 18 as the root node,
Mm-hmm.
or
That
uh,
is good thing. So you can put 18 here. So that will follows our pattern, right?
yeah.
So because if you look at like in order 2, 3, 14, 15, 16, 18, which is good. There is another option. What is the another option? You want to delete 17.
I want to delete 17. Um, I can bring 17 up to the root node, and
17 up to the root node.
no,
Okay.
okay, that is not possible.
We want to delete this node. We want to delete the 17.
I want to delete this 17. I just connect 15 with 18, or yeah, even then I have 17 which is connected with 16.
Hmm. Yeah. How can we do that? So you just said we can bring 18 to the root, right? That
Yeah,
is one solution. You can also bring 16 to the root
yeah,
because that is also possible, right? If you look at
yeah.
here, you can put 16. That still again follows the same pattern. Like if you put the in order successor, like in order traversal, you will still get the same thing. 2,
But
2, 3, 14, 15, 16, 18.
yeah, but Suresh, here 16 and 18 doesn't have any child values, so we can
Ex-
easily uh,
ex-
think like that. But what if it already have a child value, like 16 have two children and 18 have two children? How it will
Exactly,
replace?
exactly. I'm coming to that point. That is the main complexity here. So let's say we have pointed values. Let's say if you have 16, 16 has 16.5, 16.8 or something before reaching 17, right?
Yeah.
So that is the problem. So that's why we need to figure out correct value to replace. So deletion is two steps. One is finding the value you need to delete. Let's say if you want to see 17, if you want to delete 17, you will start with that root node and find where is the 17. If it is the root value is 15, you want to delete 17, it will be somewhere on the right side. That is, we already know that, right?
Hmm.
You no need to
Yeah.
go to the left side. That is a basic rule. First one is you need to go to that appropriate location, and then how to deletion. Deletion is a different aspect here. So you said correctly. So if you cannot simply bring the left node or right node into this location, that will create problems. Okay. So
Hmm.
let's say example here, let's say we have something like this, right? Let's say 20 here. Okay. Now 20 has 18 here, or which can also have 19 here, like this. Okay. 25 here. This is also in a good BST, right? So 16,
Yeah.
17, 18, 19, 20, 25. Okay. Now you want to delete 17. Okay.
Hmm.
So
Now
in
the
order to
easiest
delete,
way,
what is that?
now the easiest way is to replace 16.
Easiest way
With
16, but again 16 might also have different nodes. In this case it is good. Let's say 16 has 16.5, 16.75, 16.55. Let's say all point values.
okay.
So there could be another 10, 15, or 100 nodes under 16.
Okay.
Now the best thing is we need to find in order successor.
Okay.
The we need to replace this value. We need to replace the value which you want to delete with in order successor node. What is in order successor node? What is in order successor node is basically, if you put them in the in order, if you put in the in order, which is like sorting order, what is the next value which comes after 17? So if you are putting in order, right, 2, 3, 14,
14,
15, and
15,
then 16, and then
7,
17,
9.
18, 19, 20, 25. This is the whole in order, right?
Okay.
What is the in order successor of 17?
In order successor of 17 is 18.
18. Successor means the next value, the next
Okay.
value, which is 18. So we need to bring this 18 to this place.
7.
If you put
Okay.
18, now you can think, okay, if you put 18, what happens 19? It's not, again, there could be a lot of nodes under 18. We don't know, how many nodes we don't, right?
Yeah.
So what happens is, now the algorithm is, again, it's a recursive. So we found
But
that
18, we have to find an in order successor.
exactly. So now the problem became like smaller problem. So you want to put 18 here. Now you have to delete 18 in that tree. So initially you're deleting 17, right? Now the problem is delete 18 in the subtree. That means, again, this it will follow the same pattern. If you want to delete 18, find in order successor of 18 and then put there. Delete 17 and in order successor is 18. Now again, delete 18, find the in order successor and put that in order successor. What is the in order successor?
It's 19.
19. Put the 19. We don't we this in this tree is very simple, but there could be here, as I said, 18.18.7 here, and 18 dot, there could be a lot of values under between 18 and 19 that can exist here.
Okay.
The value which is greater than 18 and the value which is less than 19 could stay here,
Okay.
right? 18.5, 18.5, 18.7, 18.77, 18.99, not 19. So 19 is here, but there could be any value between these two can exist here. That will be the in-order successor. Let's say we have 18.7. That 18.7 is the in-order successor of 18, right? Before
Yeah.
18 and 18. Let's say 18 is the age and 19. There could be another employee which is 18 years 4 months, 18 years 7 months.
Mhm.
He is the next person, right?
Yeah.
So that's what I mean. So that is the in-order successor. 19 is not the in-order successor always. Since here there is no
More.
children here. There is no
Yeah.
children here. 19 is in-order successor. You just put 19 here. Now the problem again. Now delete 19 in this subtree because we don't know how many nodes here and here, right? At this point, there
Yeah.
is no nodes. We'll simply cancel the 19.
Yeah.
Now find, so 19 is here, 18 is here. Now
If you
write
press
the in order,
children.
make sure it follows the BST.
Okay.
2, 3, 14, 15, 16, 18. It follows the same pattern, right? After 15, 16. After 16, 18. After 18, it come back here, 19, 20, 25, right? It follows the in order pattern,
Yes.
correct? So that is the main algorithm here. So deleting a node is two-step process. First one is finding the correct location and deleting that node. This is because why are we doing here is to minimize the impact. We don't want to change a lot of nodes here. So we can do different ways here. As I said, we no need to put 18 here. We can also put 20 here. But if you put 20, you need to change 25. You need to change like a lot of changes you need to do, right? So
Mm.
the main intention here is find the correct person, find the proper, the value that can go there. So that is what the optimized solution. Optimized solution is find the next value, whatever the next value in the sorting order. You are deleting a 17. Who comes after 17. Find the who comes after 17 and put it there. That will solve the problem without changing any of the other nodes.
Hmm.
Okay, let's say if you don't have 19, you can simply put 18 here, then you are done. You don't need to do anything. Of course, since 18 has 19, you need to put 19 there,
Hmm.
right? So
Yeah.
the main intention always in the insertion or deletion is to minimize the changes, to minimize the links, updating of the links. So this is the best way. Finding in order successor is the best way.
Okay.
So you can also find in-order predecessor. There is another concept called in-order predecessor. Predecessor means the before element. As I said, you can simply, very simply, in this case, this is easier. Actually, rather than putting in-order successor, you can put in-order predecessor. Actually, you can put 16 also there,
Yeah.
because then 15, 16, and then everything will follow. 15, 16, 18, 20, everything. You just
Hmm.
deleted 17. So either you need to put the in order predecessor or in order successor. In order predecessor means the value before that value.
Okay.
Yeah. So in order successor is the very common question. So that's what we are going to discuss here. So how to delete the node. Okay. As I said, deletion and insertion always there is a possibility of changing of the root. That's why we are sending the root here, and then we are expecting to update the root. Okay, either you update the root or you don't update the root. It's up to you. Let's say if you want to delete, if you want to delete 15, then you are updating the root, right? So if you are deleting 15, you are updating the root value. It could be either you will bring the 3 there or 14. What will be the, if you delete 14, right? There are two values here. There are two choices. What is the in-order successor of 15? If you are deleting 15, what is the in-order successor of 15?
16.
16. So you can go here and you can go all the way to the down and find the in-order successor. If you have 15.5 here, 15.5, that will be the in-order successor. If
Okay.
you are deleting 15, you will put the 15.5 there, 15.5. That will be done. In this case, 16 is in-order successor. You put the 16 at the top. That means you are changing the root value. Correct? Since you are deleting root, you have to change the root. There is another thing. In-order predecessor. You can also put in-order predecessor. What is in-order predecessor for 15?
14.
14. You can put 14. That's the thing. So in either case, you are updating the root. That's why we are expecting the new root
The
here.
root.
So the delete node also returns the node.
The root.
Okay. So node with the left child only. So what are we doing here is insert 20, insert 19. We are inserting 20. We are inserting 19. So we inserted 20 here. It's already there. You inserted 19, which is I just inserted here. Now, after insertion of 20 and 19, we printed. After insertion of 20 and 19, something like this. Okay. Now, after deleting of 20, delete 20. Now we are going to delete this node 20. So in this algorithm, in this algorithm which I wrote here, we are deleting 20. If you delete 20, what will happen? So what is in-order successor? 25. There is no
25.
25 here. Actually, in this algorithm, 20 is the last one. We don't have.
Okay. So for it.
Where is the? Yeah. So node with the left child only, which is 19. So this is how it is right now. We don't have 18. We have 18, right? 17, 17, 18. Right. I think I did something here. Let's see. Let's remove this thing. 17. We inserted 17, right? Let's remove this just for just for clarity purpose. Okay. So we have something like this node, And after 18, what we did is we inserted 13. We inserted 13, which will go to the other side. Now we inserted 20 and 19. Okay, 20, we inserted 20 first and then 19. So if you are inserting, okay, I think I need to do it again. So 17 and 18. Sorry, here is the node, right? So let's say, let me going to write it. 15 here, 17 and 16 here, and 18. Okay.
18.
Okay. Now we
We
have 2 and 4
and
in
4.
this case. 3, 2, and 4. Sorry, it's
14,
almost like 9.
14, 14, 14.
So,
3 and
oh,
14.
sorry, it's 14 here. So yeah. So now we are going to we inserted 20. We inserted 20 here and 19. If you insert 20, what will happen? It will go to 20 here, right? This is 18, and now it will go. You are inserted 19. There is a 19 also inserted. It will go here 19. Okay. Now what are we doing here? Deleting a node 20. If you are node with the left child only, so you are deleting a 20 which has only left child, right? That
Yes.
is the first condition. Next one, node with the right child only, 19 after deletion. So if you deleted 20, 19 comes here. Now you are deleting 18. That's what it is. Deleting 18. Okay. Let's see. Okay, now delete algorithm. Here is the delete algorithm. So what we do is we'll get the node. If the root value is null, return null. That means you are trying to delete you're trying to delete some value, but you finally end up reaching null. That means there is nothing to delete. So you just return null. Otherwise, if the value is less than root value, right? If the value you want to delete is less than the root value, we need to say root dot left equal to delete node. And this is exactly the same the way we did before. If the value is less than, it will be somewhere. You need to delete somewhere on the left side, right? So you are
Yes.
sending root dot left. You're sending root dot left and then sending the value v.
Value.
Okay, is it clear?
Yes, Suresh. Yeah.
So if the value is greater, root dot right equal to delete node, root dot right. You are saying, okay, now we are, don't worry about left, just find this value somewhere in the right side and delete that. Else case, here is the complex part. Else means we found the node to be deleted. So the value is not less than, not greater than. If the value is not less than, not greater than, that means v equal to root dot value. Correct? Both are.
Yes.
So you found the value to be deleted. Let's say you want to delete 17 in this case. So once it is equal, right, it will come here. So now what happens? Now if the root dot left not equal to null, not left is null. If the root dot left is null, return root dot right, which is interesting here. So what we are doing here is you want to delete a node where left equal to null. Okay, let's say 18. You want to delete 18. Okay, if you want to delete 18, there is a very simple thing. You can simply take the right and put it here. That's what we are doing here. See, if the left is null, simply put the right. Else, if right is null, put the left. Okay, that means, let's say you want to delete it says like root right is null. If the right is null, put the left, root dot left. That means, let's say Yeah, you want to delete 20. If you want to delete 20, it's an example. The root right is null, right? There is no value of right. Simply put the 19 here. That will solve the issue. That's what they are saying. Like return the root dot left. Okay. So now else case here. If else case, which means node to be deleted has both left and right nodes. This is the complicated part. So the else part is here, which means left is not equal to null and right is also not equal to null. Correct?
Yes.
So this is the complex part here. So that means you are trying to delete something which has both left and
Left and right.
exactly. So this is the case. If the else case, that means you want to delete something, you found the value. You want to delete 17, you found the value, but the 17 has some left node and some right node. Now you need to find the in-order successor. That's what it is. So in-order successor equal to find in-order successor of root dot right, which is very important here. So in-order successor, it's always you need to find from the right? In-order successor means, hey, take this entire subtree and give me the in-order successor. That means it will go here and it will go all the way and find the in-order successor. Okay, let's say 18. Let's say 18 also has some node. Just an example. 18 has both left and right. You want to delete 18. What then we need to say what is the in-order successor of 18?
Inorder successor of 18 will be the left node of
No,
18.
in-order successor is always like on the right side, which is
Okay,
19 here.
yeah, 19, 19, 19.
19, right? So we are giving like, hey, take this entire right subtree, find the in-order successor. That's what we are doing.
Okay.
So find the in-order successor of root dot right. Now the root is at that location where you have both left node and right node. Now we are calling this method, hey, give me the in-order successor. Okay. Now we got the in-order successor. Let's assume I will show you how to do that. Here is the method here. But I can also show right away. So in-order successor is like this. We start with a node. If node dot left equal to null, that is the in-order successor. Otherwise, find in-order successor of node dot left. That means
Yeah.
basically it start from here. It will go left, it will go left, it will go left until you find the value null. If the left is
Okay.
null, that is in-order successor. So 19 dot left equal to null, that means that is in-order successor of the node which you are looking.
Okay.
So it will go all the way to the left. It will dig all the way until you find the right value. That's the thing here.
Mm,
You started with 20 here because 18 dot right equal to 20, right? Right dot in order successor of root dot right. So you started with 20. Now is 20 dot left equal to null? No. What is that? Now 20 dot left, which is 19. Now, is 19 dot left equal to null? Yes. 19 dot left is null. Now return 19. That will be the in-order successor of this node. So it's basically like, let's say, what is the in-order successor of 16? You started here and you dig all the way to the bottom, right? That is the in-order successor of 15. Let's say 16 has 15.6. 15.6 has 15.5. 15.5 has 15.2. Now, what is in-order successor of 15?
15.2.
Exactly. So you will go all the way. You start with right, you start with 17, but you will go all the way to the down. So let's say there could be one thing like this 15.55 before 56. There could be other nodes here. The two might have, like after two might have 15.3 because this is 15.5. The two might have something like 15.3, but this is in order successor for sure. After 15 it comes 15.2, right? We are just finding Inorder Successor. We haven't removed it. Now, what happens here is we found Inorder Successor. What are we doing here? Root dot value equal to Inorder Successor dot value. We are basically copy the contents of Inorder Successor. We cannot move the value, because if you are moving, you are changing everything. Like, you don't want to move this 15 to here, because you will lose track of 17, because 15.2 has 15.3. Similarly, if you don't want to move 19 as it is here, if you are moving 19 as it is here, you lose the track of 20. Right? What are we doing here is we are copying this content. Whatever the content 19, we are putting here.
Suresh,
Okay.
1 second. Yeah, okay, 1 minute. Baba, yeah, come and take him. Take
your
Jim.
your son came here. He also want to
Yeah,
learn. Yeah, we are almost done actually. Yeah.
yeah, Suresh, we can do.
Okay. So now what are we doing here is we are copying the contents of that Inorder Successor into this root which you want to delete. Because if it comes in this else case, means you found the value to be deleted, right? So the root is the one you want to delete. Now what are we doing here is we are changing the value, root value, with the value of the Inorder Successor. You copied the value. Now root dot write equal to delete node root dot night root dot value. Now
Value. Okay.
what are we doing here is now we have to delete the Inorder Successor. So initiate that call. As I said, you found the value, you put, now you want to delete 18, you put the value 19 here. Now you are starting, hey, delete 19 in this subtree.
So
That's
it
what
will
we are
check.
doing.
Yeah, it will check whether the 19 has the left or right side tree, and then again it will come from the first in a recursive mode.
Yep, yep.
Yeah,
So
and
we are
find an
saying, hey,
in-order successor for
exactly. We are
19.
saying root dot write. We are saying root dot write equal to delete node. So we are going to say, hey, start the same algorithm. Now delete 19. So 19 has some other nodes. We will take care. The same algorithm will work again, right? So it's a
Yeah.
kind of sub problem. Now you copied the contents of 19 from here to here. Now you want to delete 19 in this subtree. That means root dot write equal to delete node root dot write comma root dot value. That means root dot write is whatever the value here, which is 20. So you starting from 20, try to delete 19. Okay.
Okay.
So finally, after all these things, we simply return the root.
Root.
Yeah,
Yeah.
this is how it is. It's complicated, but if you
Yeah.
are
Root is a bit
understanding
complicated.
line by line, and why it is doing, how are we going to do, that's the magic here. Okay.
Yeah.
So I think we just ran before. If I show the output, where is the output here? Yeah, I can bring like this. Yeah. See, after deletion of 20, we deleted 20, which is at the end, which is simple. Deleted 20 is simple. Now deleting 18. After deleting 18, 19 comes here. Okay. Now if you want to delete any other middle nodes, that the magic will comes. So we can also try deleting probably 15. We can try deleting 15. This is root node, right? You can also do that. What will happen if I want to delete 15? Node with the right, node with the left, and right childs. I'm deleting. Okay. After deleting 15, it is root. What will happen? Let's see. Now N15 may have something else. N15 will have probably the value 18. No, 16, maybe 16. Yeah, in this case, yeah, if you are deleting 15, 16 will go to the top, right? Let's see.
16 and then 16, 17.
Did you understand the algorithm here?
Yeah.
Yeah.
Delete is bit complex, but I have to practice it. That's it.
Yeah, these three lines are very important. First one is like, finding the Inorder successor and copying the contents of Inorder successor and then deleting the Inorder successor. Basically, you are deleting that successor. So now here we found 19. Let me remove all this. Let me remove this. We completed all this. Delete 15. Okay. All the way. Delete 15 is here. Okay. Oopsie. This is insert node. Huh? Okay. Let me remove this. Breakpoints. Okay. Yeah. So now we are saying delete, like we are sending 15 and we are asking to delete 15, right? The 15 has both the left node 13 and right node 17. Let's see what happens if I just complete the algorithm. Let's see. Now N15 has 16. See that?
Yeah,
Now root is updated with 16.
yeah.
16 has root 18, 17 has the right, and 13 has the left. So now if you want to print it, let's see. If you print, you can see it's already printed. Here is the value. So 13, 14, 16, 17, 19. So that means 13 is the left and then 14. That means 13. This is the one I think. 13 is here. This is 13, right? 13, 14, and 16. 16 at the top. 16 because you removed 15, right? 16 comes here.
Now
16.
16 is the root.
16 is the root. 17, 19. 17 is here and 19 is here. Simple, right?
Okay.
So that's how it is. Basically, Inorder successor. Finding Inorder successor is very important, and it's just two lines actually. Even it's like finding Inorder successor is not difficult. The only thing is finding Inorder successor always starts with right. Take the right value, take the root dot right, and go all the way to the left. So 15. If you want to find Inorder successor of 15, just to take the right value and then go all the way to the left. Okay.
Way predecessor will take the left value and all the way to the right.
Exactly. That's a really good point. So if you want a predecessor, take the left value 13 and go all the way to the right. That will give you the predecessor of 15. Yes,
Yes.
you're absolutely right. So you can also try that. So fine. There is a two ways to do it, right? You can replace either in-order successor or you can find the in-order predecessor. You can also do that. Yeah. And then here, once you copy the in-order predecessor, you start from the root dot left, you need to delete that value. So always this will change. That's it. Right will become left and left will become right. That's the only change. Yeah. Cool. That's it pretty much. So I hope we understand it, but I can send the algorithm
Yeah,
and
yeah,
you can
Suresh.
get the code. Okay.
Yeah. Thank you,
Cool.
Suresh. Thank you for the session. It was
Yeah,
great.
it's been like late already. Yeah. Thank you for coming and have a nice week ahead. Yeah.
Thank you.
Yeah. Thank you. Bye.